Thank Chairman. Good afternoon, everyone. And firstly, I want to thank HKI and its organizers for providing such a wonderful opportunity to present our work. And I am FU Yuchen from the Department of Physics, and my supervisor is Dr. Chai Yu. Today, I will share work titled as Taking Advantage of Aggregation to Chaperone Nanoparticles Across Fluid Interfaces. To begin with, I'd like to give a short introduction on its background. Nanoparticle phase transfer of nanoparticles is of great interest in both academia and industry due to their applications in the fields such as nanoparticle synthesis and the catalysis reactions, the theranostics, biology, etc. And this generally, nanoparticles can classify into the organic nanoparticles, mental nanoparticles, and non-mental nanoparticles. These nanoparticles covered with functional ligands or polymers can transfer from one phase into another by switching their surface wettabilities. And this figure lists the general methods for realizing the nanoparticle transfer between the aqueous phase and the organic phase, such as by ligand exchange by the host gas interactions or by Janus particles. And one more thing I want to introduce is the controllable molecular diffusion by the interfacial jamming. As this figure shows, after compressing the droplet volume, the wrinkles appeared on the surface as a sign of the jamming interface formed by the assembly of the nanoparticles and the ligands with the electrostatic interactions. And many reports have shown that the diffusion of the molecular cargoes can be controlled by tuning the jamming and unjamming state of the interface, which lays the foundation for the following work, which I will describe later. So let's come to the main contents. So the first question is, what's new in our work? This figure shows the conventional methods. This figure shows the conventional methods for nanoparticles transfer from the aqueous phase into the organic phase. Here we use the good nanoparticles as our research model due to its unique surface plasmonic properties. And previous research believes that the aggregation of nanoparticles can lead to the failure of the transfer. So they functionalized the nanoparticles by adding the surfactants, the phase transfer agents or something like that into the aqueous phase or the organic phase under the external forces, such as the vigorous blend, to avoid this aggregation. In our work, however, by using the amino terminate PDMS as the ligand, the transfer process undergoes the nanoparticles aggregation in the aqueous phase, and then sedimentation of these aggregates as the interface, and finally redispersion of the nanoparticles in the organic phases. So let's see what we've got. This figure shows the microscopic observation of nanoparticles transfer by using the DCM containing the amino-terminated PDMS with different ligand concentrations. The phenomenon match well with the mechanism we proposed earlier. To gain the further insights into the nanoparticles aggregation in the aqueous phase and the gradual transfer of the nanoparticles in the organic phases, we conducted the in situ UV spectroscopy by using this experimental setup. So in the aqueous phase, the peak assigned to the aggregation increased at first and finally reduced to 0. And however, in the organic phase, the characteristic peak of the gold nanoparticles started to appear after 20 days. And we also measured the spectrum of the aqueous phase and organic phases. As expected, there's no signals on the there's signals of the observed on the aqueous samples. However, a characteristic peak could be seen in the organic phases with a higher ligand concentrations. And based on the above results, we proposed that the nanoparticles aggregation is reduced by the diffusion of the ligands from the oil phase into the aqueous phase. To prove this, we measured the evolution of the surface tension of this aqueous droplets after contacting the ligands for some time. And this result showed that the ligands can diffuse into the aqueous phase, and the diffusion speed can get much faster in the presence of the gold nanoparticles. And the interfacial tension measurements give some more direct proof of this ligand diffusion behavior by the reduction in the IFT values of both water and the gold nanoparticle dispersion when they contact with the ligands. And we also measured the DRS of the gold nanoparticles before and after phase transfer with the average size of the particles as 32.4 nanometer and the 30.4 nanometer respectively. To get a clear view of this single particles aggregation and single particles process, the TM measurements was conducted. After analysis of the particle size distribution, the average size of the particles before and after this transfer as 32 nanometer and the 31.6 nanometer respectively, which are in good agreement with the results of the DRS. And to test the universality of this mechanism, we also used the other dense organic solvents, such as the chloroform, the carbon tetrachloride, and other similar amino PDMS with a different molecule weight, like the 3K and 2K. All the samples experienced the same process from the initial single particles in the aqueous phase and to the aggregation, and to finally the single particles in the organic phases. which shows the universality of this method and the potentials for broad applications. Since the citrate molecules on the surface of the gold nanoparticles can be easily stripped off by these amino-terminated PDMS, through this through this ligand exchange, rather than interact with each other by the electrostatic interactions. So here we used MUA functionalized gold nanoparticles in this system, which can only interact with the ligands by these electrostatic interactions. We use these MUA gold nanoparticles to contact with the different ligands like the CTAP, the 2K PDMS, the 3K PDMS, and the 27K PDMS. And we observed that in the cases of this 2K PDMS and the 3K PDMS, the aggregation of the nanoparticles occurred in this aqueous phase. However, only in the case of the 2K amino PDMS succeeded in transferring nanoparticles into the organic phases with a rather faster speed. Inside to UV spectra, all this aqueous phase give a more direct view of this particle behavior on macro scale. And this all consistent with this phenomenon we observed here. Next, we also summarized the spectra of all the gold nanoparticles that are successfully transferred into the DCM phase. And we found that the nanoparticles covered with low molecule weight ligands had a more obvious redshift than that covered with higher molecule weight ligands. This is due to the difference in the dielectric constant of this ligand layer. And we also use one particle model to describe all the processes in this work, just shown here. As I mentioned earlier, the diffusion of the molecules can be controlled by jamming the nanoparticles at the interface. So inspired by this, we introduced another charged nanoparticle, the PS nanoparticles into our system. So when the nanoparticles contact with the solvents containing these amino-terminated PDMS ligands, the PS nanoparticles rapidly assemble and jam at the interface to stop the diffusion of the ligands into the aqueous phase. We also made a demo to illustrate this. Compared to the severe aggregation in the aqueous in the gold nanoparticle dispersion, the mixed nanoparticle dispersion shows no obvious aggregation after contact the ligands for half an hour. To get more evidence for this, we also conduct the IFT measurements after equilibrium for 20 minutes, compressing the droplet volume get all the got nanoparticle dispersion, got no wrinkles on the surface of droplet. However, compressing the droplet volume of the mixed nanoparticle dispersion resulted in the wrinkles on the surface, indicating that the jammed solid-like film was formed at the interface, which can block the diffusion of the ligands into the aqueous phase. So finally, I want to thank my supervisor, Dr. Chai Yu, and the Professor Thomas Russell for the guidance and suggestions on this work. And we also, and at the same time, I also want to express my gratitude to our collaborators, the Professor Lei Dangyuan, Dr. Wang Yufeng, and Dr. Gu Peiyang for their suggestions on the work. And I also want to thank my lab members for their support during the experiments. And also want to thank the NSFC and RTC for providing the financial support to our work. So thank you for all your attention. Thank you.